Right, so here we go with A2 Physics from CCEA, and this is Fields and Their Applications from June 2016. Let's get started. Question 5. Electromagnetic tethers are a method by which electricity can be generated in space. Essentially, a satellite or spacecraft allows a long conducting wire, the tether, to extend from it as it orbits. The tether tends to hang in the vertical position, and as the satellite orbits, sweeps through an effective area of the magnetic field. Calculate the electromotive force EMF induced across the ends of a 25 kilometer long tether orbiting with a velocity of 8.21 times 10 to the 3 meters per second, where the horizontal component of the Earth's magnetic field is 4.01 times 10 to the minus 6 Tesla. So, we have an equation that says that the EMF that you get is the delta of n phi over the delta of time. Now in this case, we're really talking about the delta of nBA over how long that took. So there's only one strand of wire, and it moves forward at a velocity so that it covers a certain area as it moves forward. So it sweeps out this area as it moves forward. So if we imagine the area swept out per second is going to be delta A over delta T, that's going to be just the area of this rectangle in 1 second, which will be the velocity, because that's how far forward it goes per second, times the length of it. So delta A over delta T is just going to be VL. Now n equals 1 because there is only one strand, and we just multiply that by B then, and we get that the EMF is BLV. So B is 4.01 times 10 to the minus 6, L is 25 times 10 to the 3, and V is 8.21 times 10 to the 3. That will give us the EMF produced on the wire. And putting that through the calculator, I get 823 volts. Part B. A certain mobile phone charger steps down the mains voltage from 230 volts using a transformer which has a primary coil of 1104 turns and a secondary coil with 24 turns. Assuming the transformer is 100% efficient, calculate the output voltage across the secondary. So we need to use our turns ratio equation for this. NS over MP equals VS over VP. And so we know all of those things except the one VS that we're trying to find, the voltage at the secondary. So it's going to be NS VP over NP. And we just substitute into that from the numbers we have been given. Okay, so we've got 24 times 230 divided by 1104, and that gets us a voltage of 5 volts. Part 2 then, transformers operate at a high efficiency, but there is still some energy lost, and for a mobile charger the voltage across the secondary is actually 4.6 volts and the current goes from 0.26 to 1.1. Okay, so efficiency, remember, is power out over power in. And so we need to do VS-IS, which will be the power out, over VP-IP, which will be the power in. And then we just substitute our values. So we've got 4.6 times 1.1 and 230 times 0.026 on the bottom line. And if we put that through the calculator, we get a value of 0.846 roughly. And so 0.85 to 2 significant figures would be fine. Question 6. Figure 6.1 is a simplified diagram of the inside of a cathode ray oscilloscope, or CRO. The dashed black line represents the electron beam. Part A1. Complete Table 6.1 by naming each of the components identified in Figure 6.1. So I've brought in the little picture here, and we have to identify these components that are in the diagram. So this is your filament for producing a hot cathode so that we can produce electrons by thermionic emission. This is your anode, your positive anode, or you can call it electrode if you want. And then we have our deflecting plates. 3 are the X plates, they deflect in the horizontal direction, and 4 are the Y plates, they deflect in the vertical direction, and 5 then is a fluorescent screen. So heated cathode, electrode or positive anode, X plates, Y plates, fluorescent screen. So heated cathode, positive anode, X plates or horizontal deflection plates, Y plates or vertical deflection plates, and some kind of fluorescent screen. Explain how the CRO can be used as a measuring instrument for voltage. So we have a vertical deflection of the beam, and that depends on the setting on the Y gain amplifier, the Y deflection amplifier. So the voltage input is multiplied by the Y gain amplifier setting. And so if you compare the number of squares of vertical deflection with the Y gain setting, you should be able to convert it back to a voltage. So we take the deflection and multiply by the Y gain setting, and that gives us a voltage. Part B. In this CRO, the moving electrons are deflected by electric fields. Consider the situation illustrated in Figure 6.2 where an electron enters a uniform electric field horizontally at the midpoint between two parallel plates that are 80 millimeters apart, with a velocity of 5.6 times 10 to the 7 meters per second. The top plate is at a potential of 2.5 positive relative to the bottom plate. Calculate the vertical displacement of an electron at the end of these plates. Okay, so this is a projectiles problem, very much like the one you would have with G pointing down. You get a U-vast vertical problem here, where the acceleration in the vertical direction can be got by the electric force over the mass of the particle. So you can say from Newton's second law that F equals ma, and therefore A is F over m. So that's sort of a starting point. If F equals ma, then A is going to equal F over m. Now the force on a charged particle in an electric field is going to be EQ. So in this case it's big E, little e, where little e is the elementary charge, the charge you would find on an electron. We're told that this top end here is positive, 2.5 kilovolts. So the electric field points down, and that means that the force on the particle points up, and that's why it swings up, because the force on a negative particle is opposite to the direction of E. E points in the direction of a positive particle, the force on an electron will point opposite to the electric field. And E flows from positive to negative, so E points downward in this case, so F points upwards. So we need to write a U-vast list for this. So the important bit in the U-vast is this idea that vertical initial velocity is nothing, vertical final velocity is unknown, A is F over m, and F is E times the charge, electric field times the charge, divided by the mass of the particle. In this case that's the mass of an electron. S is a thing that we're very much interested in, and T is a thing that we don't know. So this is where we're going with this. We need this vertical deflection. Now T can be obtained if we look at the horizontal behavior, because the horizontal motion at this speed will continue until it crosses all the way through. So the time in here is going to be related to this horizontal motion and how far it had to go. So the time in the plates is going to be the horizontal displacement divided by the horizontal velocity. And that works out at 2.14 times 10 to the minus 9 of a second. Now for a parallel plate system, this E can be got by dividing the voltage by the distance between the plates. Remember, we do know that it's 2500 volts, 25 kilovolts here, or 2.5 kilovolts, 2500 volts, and we do know that these plates are 80 millimeters apart, so it is possible to get E there, or we can just substitute in for our A, so our A would become VE over DME, where that's a subscript E, that one there, that's a little e, this one. So voltage times the electron charge divided by the distance between the plates times the mass of an electron. Now a word to the wise, CCEA seem to give intermediate marks for you working values like this out. So when you're doing this, you may want to stop at points and work out like what the value of the acceleration is. It's not terribly good practice to work intermediate values out, because their faults in them can then propagate through all your other answers. So CCEA seem to, however, have a little habit of giving marks for these things. So you should probably work these out separately as well. So this vertical displacement here can be got from half ut plus half at squared. So u vertical t plus a half of a vertical t squared. And u vertical is nothing, so s vertical becomes a half times a times t squared. And so it's a half times VE over DME multiplied by t squared. So that comes out to be a half. So stick with me here. Okay, so we've got a half times the voltage times the charge of an electron. Bottom line, we're dividing by 80 millimeters, 80 times 10 to the minus 3, and the mass of an electron, which is 9.11 times 10 to the minus 31 kilograms, and then we're multiplying all that by t squared, which is this 2.14 times 10 to the minus 9, but we must also square it. And I'm getting a value for that of 0.12567 of a meter, so I'm going to call that 0.126 of a meter. And that is that. Quite fiddly, but remember that it is a projectiles problem. The only thing you need to do is get an acceleration, whereas in a normal projectiles problem you just put g in here. We need to find the electric properties, so you need to know that it's F over m from Newton's second law. F is E times electric field times charge, and electric field can be got from V over D in a parallel plate case. So it's V over D multiplying by the charge dividing by the mass of the particle. That then gives us an acceleration value, and so this A is the important part. And obviously go into the horizontal problem to get the t, so we can put in t squared. That's everything then. Thanks for watching.